Okay, so in the last video we talked about distribution theory and how we don't want to evaluate at specific x values anymore. We want to evaluate functions in areas. So we had some little function, and we said, okay, we want to evaluate it in this area. But we kind of left that blank and said, so what does it mean to evaluate a function in an area? And so basically what that means is integrate, right? Um, so I've got Desmos here, and I'll just show you what I mean. Um, so first of all, I'll show an example of a function with a hole in it, right? So we'll make a piecewise defined function in Desmos. If x is less than 1, we want the function to be x, and then whoops, I want a colon there. We want it to be x, and then if x is greater than 1, we want it to be x as well, and then otherwise we want it to be 2, right? So we want a little hole in the graph. But what happens in Desmos is it doesn't really show you the hole at 1. So we need to make this a little bit different. We need to make it so like this would be about zero point 0.9 and this one's going to be about 1.1, just so we can have this actual gap here and show something visible. But that's pretty big. So let's just make it 0.99 and then 1.01, right? So we narrowed that gap a little bit. So that's a lot smaller, but it's still, in the context of measure theory, I mean, that is not almost nowhere. I mean, that definitely, this x value has some measure, which is, exactly what, zero point zero 0.02 or something. Um, so yeah, so this isn't an exact, but it's just a way to give us some visualization in Desmos. So I'll just name this f of x. Okay, so there we've got our function. And, what we're saying is we want to be able to evaluate this function, but not at individual points, because if so, we're going to have ourselves a little problem here. But we want to evaluate in areas. So how do we do that? What we do is we say, um, we're just going to do like an integral, right? So an integral is the basic way of evaluating over an area rather than just at a single point. So I'm going to make us just some little slider here. I'm actually going to move it above our integral. Um, and so now I'm going to evaluate at at this d value plus or minus zero point zero 0.01. Actually, I'm going to minus zero point 0.1 and then d plus zero point 0.1, right? And we're going to evaluate that, or we're going to evaluate f of x in that area, right? So now I'm just going to make a little point. It's the x value is going to be d, and the y value is going to be, I'm going to call this a equals, and the y value, this is going to be a, right? Okay, so now if I move this slider, you'll see we're evaluating this function, not at a given point, we're evaluating it at an interval around d. And you'll notice this y value is obviously not the same as this y value, and I'll get into that in a second. But basically, this is doing what we want it to do, right? So hopefully what happens when we move d, when we move this to about zero point 0.1, we don't feel this jump as much, right? Because if we're plugging in values to the real function, we feel a huge jump right there. But that's what we're trying to avoid. Um, and so if I move this over near zero point 0.1, did you see? It hops a tiny bit actually, but not much. Actually the reason it hops at all is because this is some non-zero measure interval, right? So if I make this even more narrow, which is almost so small you can barely see the point, if I drag this, you'll no longer be able to see it hop really at all. Let's see, maybe a little something there, but that's the kind of the spirit of what we're doing here, and I'll show you how to get this to line up here in the next video. So.